So I guess today's lecture 8. So we have 8, 9, and 10. So we have 3 lectures left, including this one. We'll get to the Poincare conjecture. We'll probably discuss more about that near the last lecture. There's still some preparations that need to be made so that it ends up making more sense. For now, I think we're going to keep talking about curvature and other cool things related to that. Now it has been a while since I last saw you, so let me just quickly remind you what was this deal about the curvature. But yeah, I hope the seminar has been somewhat relaxing compared to all your other courses that have probably tons of assignments. So what we talked about last time is was curvature, if you remember it. So the idea about curvature was like, first of all, if you, I don't know if anyone remembers the formula, but if you had a circle of radius r, the curvature of a circle of radius r was 1 over r, right? Which meant that as the circle becomes bigger and bigger, then the curvature of the circle is smaller. So a circle curves less as you increase the size, the radius of the circle. And then the trick was, if you had a curve, like an arbitrary curve, right? At every point, you could find something that is known as an osculating circle. And then the idea was that at those points, like say this is a point P, this is a point Q, this is the point R, the curvature, well, maybe I should not call this R. The curvature of a point P is basically it's essentially the 1 over the radius of this circle. So it's basically 1 over the radius of the oscillating circle. And again, strictly speaking, the curvature could be positive or negative, just because like somehow it also takes into account how the curve is bending. So that has to do with concavity, which you may have seen if you have taken calculus 1 before. If not, it doesn't matter. I'm just saying that the curvature, strictly speaking, like you can sort of say, oh, curvature is +3, or also curvature is -3, and that is related to how the curve was bending at that point. So you can also think of the curvature as being the curvature in reality can be positive, negative, or 0. And then when we had surfaces, is this okay? So far so good. Everyone more or less remembers this. This was like what curvature for curves meant, right? Is this okay? Good. And then when you have surfaces, The idea was like, for example, let's just do it in two quick case examples where this is easier to illustrate. Like, say for like if you wanted to find the curvature of the sphere, like the way in which was defined, is that you would look at a point on the sphere, say, for example, the North Pole, and then there are like curves passing through this point, right? For example, you can think of the longitudes or like the meridians. So you have there are different curves passing through the North Pole. So like what you would do is like you consider the curves passing through a given point, and then you look at among all these curves, there's one with the smallest and largest value for the curvature. So among these curves, there's one with the largest possible value of the curvature. And the other with the smallest and another with the smallest value. And then the curvature is just the curvature at that point for the surface. It was just the product of those curvatures, and then the curvature at P is then the product of these curvatures. So essentially, like, for example, for the sphere, like the curves that you end up looking like at are like these meridians. And so they are like sort of circles. Okay. And so meaning that since they're circles, each of these possible curves has curvature 1 over r. So they'll end up having the same value in this case. And so the curvature at P is just a product of of two of those curvatures. So curvature at P is just 1 over r times 1 over r. So it's 1 over r squared. Okay. And if you look at something like the plane, if you look at the plane, then like the curves that you end up looking through, passing through a point on the plane are just like straight lines. And then the curvature of a line, as you might imagine, is just 0. So the curvature at P happens to be 0 times 0. So that gives you 0. And essentially, this is one of the reasons why on the torus, where's my friend the torus? Well, I have it there. But like on the torus, like the donut, you can sort of also find curvature which is 0 because the donut, remember, could be obtained like sort of from the plane just by gluing together like the opposite edges. So this one also has curvature 0. Okay. And the main idea is that like the reason why curvature is so interesting is that if you look at the total curvature of the surface, the total curvature, again, like that fancy way of saying that is like the integral of the curvature. Like you sort of add up all the curvature of the individual points. But that's not too important for us. Just think about like the bulk amount of curvature. If you look at all the total curvature, then that is equal to 2 pi times the Euler characteristic of the surface. So in other words, remember, I don't know if you remember, I mean, it has been a while, but what I'm saying is that the total curvature is really 2 pi 2 minus 2 number of holes, because remember that was the formula for the Euler characteristic. Okay. So it's essentially, this is saying that the number of holes of the surface determines like the total amount of curvature on it, which is kind of amazing. And so like what I'm trying to say is, like, for example, if you can make a list with the surface and its total curvature, and so again, like for the sphere, there's 0 holes, and so you get 4 pi times 2. Sorry, you get 2 pi times 2, which is 4 pi. For the donut, there's 1 hole, so you get 2 pi times 2 minus 2. So that's 2 pi times 0. That's what that gives you 0. But then if you have 2 holes, right, you get 2 pi times what? 2 minus 4. So that's -4. That's minus 4 pi. And then if you have 3 holes, you get 2 pi times what? 2 minus 6, which is -4, and so you get -8 pi. And I don't know if you can see what's happening as you add more and more holes, right? This becomes more and more negative. So after 2 with 2 more holes, right? That means that the total curvature is negative. Is this making sense? And like, there's only one example, which is a sphere where the total curvature is positive. So you say that the sphere is a positively curved space. There's only one where the total curvature is 0, and in fact, you would say that the torus is a flat space. And interestingly enough, I suppose you could call these negatively curved spaces. That's probably a terminology that's used more often by physicists. In this particular case, they're also called hyperbolic spaces. So in summary, what you need to know, like, is of all the possible surfaces in the world, one has like total positive curvature, another has like 0 total curvature, and the overwhelming majority, all surfaces except 2, have negative curvature. Is that making sense? And so in a sense, like if you were going to a zoo of spaces, right? You went to a shopping store about spaces, you have an aisle where you can purchase a toy of a positively curved universe, another aisle for flat universes, another aisle for negatively curved universes, and the flat and positive curved universes are sort of alone. There's only one toy to choose from, but you could like choose from infinitely many negatively curved spaces because you know you can increase the number of holes as much as you want. You can have a surface with 1 million holes, and that would have a super negative curvature. In a sense, like the vast majority of surfaces are hyperbolic or negatively curved. And in fact, again, if your one's interest is for three-dimensional universes, like because our space has 3 dimensions, there's something analogous there that happens in the sense that for 3-dimensional universes, most universes are like sort of negatively curved in a similar sense. So like the takeaway here, so the lesson to learn is that most 2-dimensional universes have negative curvature. And again, that remember that means, for example, that in those universes, if you draw a triangle, the angles add up to what, like less than 180 degrees, for example. Okay, so most universes have negative curvature, and in fact, there's something similar that happens for 3-dimensional universes. In the sense that most of them also have negative curvature. Is it no? Does anyone know why we eat pizza the way we do? So eating pizza is a mathematical problem also. Oh, by the way, I did send you did I send you the email about like Pi Day? I created like an announcement. Maybe you didn't receive it. Oh, if I didn't, I will send it again. There was a nice video. You know, Pi Day was on March 14. There's an announcement. Okay, good. You can check the announcement if you want. So Pi Day is March 14 for, I guess, obvious reasons if you think about it. And then there's a video about like how people computed pi in the past, which is sort of fun. If you haven't watched it, I recommend it. But now I'm going to talk about a different pi, which is a pizza pie. So let me show you a video, which is I think kind of fun, which actually illustrates some unexpected consequences of this notion of curvature. So let's, it's a short one, but I like playing those videos because I think it's a useful way to look at things. Can everyone see the yes, our friend from the past? I don't know if you remember him.
So how come we eat pizza the way we do? You know as well as I do, if I just hold it like this, it flops over. And you know as well as I do that if I curl like this, I can eat. So why do we eat pizza like this? Gauss. Gauss tells us why. What does Gauss have to do with it? Gauss came up with this absolutely nifty theorem called the Theorem egregium, also in English called the remarkable theorem. Curvature is an intrinsic property of surfaces. Curvature, we all kind of know what a curve is. What's curvature? This piece of paper has no curvature at all, right? It's flat going this way, flat going this way. We'll come back to that. What about a sphere? Well, a sphere clearly has curvature going outward this way and outward going curvature this way. If both curves are outward, Gauss says, oh, multiply them together. This is a positive, this is a positive, positive times positive means, oh, it's a positive curvature. So this is positive curvature right here. Everywhere on a sphere, it's positive curvature. What about a banana? For a banana, I see along here, it's curving out. Along this way, it's curving out. So this is positive curvature. But watch this, watch this. Over here, oh, it's curving outward along here. We remember that. But along here, it's curving inward. So this one is a negative Gaussian curvature. This one is a positive. A positive times a negative means that at this point, I have a negative curvature. So someplace along a line here and along the line here, the curvature of a banana changes from being positive Gaussian curvature to negative Gaussian curvature. For a torus along here, it's curving outward. That's cool. Along this way, it's curving outward. Outward times outward is positive. So that's positive. But over on the inside, over here, it's curving outward there, but inward here. So this means this is negative curvature. So there's negative curvature around here, positive curvature. So someplace around this line in a torus and along someplace around here, it goes from negative Gaussian curvature to positive. That makes sense to me. What Gauss said in his remarkable theorem, this curvature is intrinsic to the surface. So if I have something that starts out with a certain integrated Gaussian total curvature, then no matter how I stretch it and turn it around and move it, it's going to stay the same. I know that this piece of paper starts out flat. If I bend it, I'll draw a line here. I'll bend it sort of along that line. Okay, along there, in this direction, there's negative curvature. But along here, so there's minus going along there, but this has still zero curvature. So it's a straight line. It's a straight line going that way, but going this way, it's negative curvature. Flipping on the other side, look over here. I still have no curvature in that line, and I have positive curvature over here. Well, what's the Gaussian curvature right at this point right here? It's some positive number times 0. Gauss tells us that Gaussian curvature, the multiplication of this direction curvature and this direction curvature is intrinsic to the surface. That means that if I bend it this way and I get positive curvature, at this point, since the surface started out with no curvature, flat, no curvature at all, that if I add positive curvature here, I'd better multiply that by something that has 0 curvature, which is a straight line. So if I have curvature in this direction, I'd better have no curvature there. What about a pizza? Come here, Brady, come here, come here, come. If I have a flat pizza and I lift it up like this, it's going to bend down. If it bends this way, then, oh, there's Gaussian curvature is positive here, but I have 0 going this way. But I can take advantage of that by saying, I will make this have no curvature along here and negative Gaussian negative curvature there. So at each of these points, curvature stays the same. If it tries to flop this way while I'm curving it this way, the pizza would be violating Gauss's remarkable theorem. Pizzas don't like to do that. We'd like to thank the great.
Let's see. Well, now you know how we eat pizza. Did that make sense? Good. So now you see this course is teaching you practical things, how to eat, important lessons. So let me do a quick poll. Okay, for some silly reason, the poll is not whether or not you took already calc 1. I mean, it's just like I don't know how to change the question. Let me end it and restart it. Like, so the poll is actually whether or not you know what a vector is. So the question about calc, change it with vectors and answer whether or not you know what a vector is. So yes, if you know what a vector is, no, if you haven't heard of it, which is totally fine. I'll explain it in any way. Okay, good. I think among those who voted, the overwhelming majority knows what a vector is, but that's fine. We'll say a little bit about that. So let me explain to you what a vector is. So really the way to think about vectors is that they just are arrows in space. So all these drawings represent vectors. This is also a vector. 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 Okay. And then there are things you could do with vectors if you want it. Not that we need them, but for example, if this is a vector, which is sometimes denoted with D with an arrow on top of it, just to say that it emphasizes a vector. 2 times D means an arrow pointing in the same direction as V, but twice as large. Okay. And then if this is one vector, and this is another vector, then you could also add them together and you get a new vector, which is called V1 plus V2. Okay, so these arrows can somehow be added. But like the only thing that you need to know is like that when I say vector, just think about arrows. Okay, so there's a mathematical way to represent them, but I don't want to get into the nitty-gritty of that. I just want you to make pictures. So there's a thing called a vector field. And a vector field just means an arrow at each point in space. An arrow is drawn at each point in space. So my favorite example to give in multivariable calculus for what a vector field is anyone remembers the river in New Brunswick? What's the name of the river? Good. So imagine you're playing with a paper boat on the river. It has to be something small so that it won't distort the motion of the water. So it has no engine, nothing. And you just place it on the surface and the boat will just follow naturally the water currents. Okay. So if you place it on a specific point, you can draw an arrow that tells you, well, that's the direction where the boat wants to start moving in, right? But say if I put it here, maybe the boat wanted to move this way, right? And maybe you are unlucky and there was something interesting happening with the river, and you when you put it here, something like this will start happening. Everyone says what's the problem. I mean, if you are on that boat, that's a problem for you, right? If you had placed it here, because that means that you're going to start getting trapped in this vortex, right? Everyone sees that. Is that making sense? And then if you're an oil company, or any other company, maybe you're dumping some liquid of unknown nature into the river, right? And so since you're introducing liquid, right, things like are being pushed away from the point where you put the big hose into the river, right? Um, and so as you might imagine, like this is sometimes called like something like this would be called like a source, right? Because like somehow you're creating fluid at that point. You could be lucky, and maybe you wanted to take a break and you are able to put the boat exactly at a place where if you place it there, then the boat just stays still, right? Uh, Meaning that somehow the water stopped there, like it's stationary at that point, the water. So that's called a stationary point, right? So stationary point where the boat would not move if placed there. Okay, that's also called an equilibrium point in physics. Is that making sense? So for example, here's like a reason why this would call, like this is maybe a better example of an equilibrium point. Right, imagine like now instead of a boat, imagine you have like a snowball, right? If you are able to place a snowball really at the top of the mountain, right, then it will stay there. And also if you place it at the bottom of this valley, right, it would also stay there, right? So both these 2 points would be called equilibrium points, right? So P and Q are equilibrium points. Is that making sense? But then there's one, I mean, not that this matters too much, but it's still interesting to at least discuss this. There's one called, like, there's one that will be stable and the other which will be unstable. Okay, so which one? The stable one means that if you had moved the ball a tiny amount, right, then the ball wants to return to its location. Which one is the stable one in this case? Good, good. Right, because if you put the ball, imagine you sort of kick it a little bit. What are the vectors in this case? The vectors which tell you where you're trying to move. If you had kicked it in any direction, right, the vectors are sort of trying to point back to where it was. But if you kick it here in any of the 2 directions, right, then you don't want to return to that point. Is that making sense? So this one is called unstable equilibrium point. But then so let me, I mean, let me go back to can everyone see the GeoGebra thing?
Yep.
So if you go to GeoGebra, I mean, again, there's a mathematical way to write these vector fields, and I don't want to spend too much time doing that. If you want to learn that, then you can take multivariable calculus. But just imagine that you sort of can put like different arrows in space, right? And depending of which formulas you use, I mean, there's like, again, like a way to write these formulas. but depending on which arrows you draw, I mean, depending on which formulas you write, you get different arrows. Okay. So let's focus on a simple one, which is this vector field again. So once again, like if you think of all of this as representing like a river, this would be like the direction that a boat would take as when you place it at that point. Okay. And so as you see, essentially, we can zoom in, or we can even draw more arrows. They're pointing away from the origin, right? There are different ways to represent them, but the idea is like they get really, I mean, they start getting smaller and smaller at the origin. Again, if you look at it from the formula, I'm not explaining how they are found, but like at least if you put x equals 0 and y equals 0, I mean, you get 0, 0. So that's saying that at the origin, the vector is of size 0, which means that it's like just a point. So it's like stationary. So at a vector field, like you can look at the points where it vanishes. Okay. So let's go back to that. So what I'm saying is that I just drew like what I was drawing was a vector like this, right? A vector field, sorry, like this. So it's pointing away from the origin. And the origin, the point P, the origin 0, 0 is an equilibrium point or a stationary point of this vector field. Okay. Is this making sense? Everyone agrees with that. It just means that that just means that if you happen to place the boat precisely at the origin, the boat will not move. Is that okay with everyone? Now, there's a thing that you can define for a stationary point called the index. Okay, so and the way in which it's defined is the following. So imagine that you choose like a circle around the stationary point. Okay, here's like what you do is you draw a circle centered at the stationary point. Okay. You at each point of the circle, you look at the vector, you look at the arrow, and make a copy of it at the origin or at this and move it to the origin. So what do I mean by this? Like, I think this is better. Let me stop here before continuing. So what I'm saying is like, we have two pictures in mind. So what I'm saying is like, we drew, again, like our vector field look, I mean, we had a circle, and you pay attention to the arrows on this circle. So how the arrows look on this circle. So I'm just going to draw those here. Okay, so let's say, for example, at the point P, here's, well, let's call it N for North Pole. Yeah. Well, I think I'll run of letters. So let's call it A. So at the point A on the circle, right, we had this vector. And I'm just going to drag it and copy it at the origin, okay? So this is like the arrow corresponding to the point A. And the point B, right? You have this other arrow. And now I'm going to drag it and place it at the origin. At the point, let's keep some steps, like say at the point C, you had this other arrow, and now I'm going to drag it and put it here at the origin. And say, for example, let's do two more. Here you have at the point D, you have this other arrow. And then here you have, say, let's make this the last point, E. You have this other arrow. Is it more or less clear how I'm drawing the arrows from here to here? And what we have to look at is how many, and the index, right? So what I'm saying is, like, imagine you're walking along the circle from the point A, and you do a full revolution, right? And so you do a full revolution, and then you count. I mean, when you walk, when you return to the original place, right? As you are moving along the circle, you're drawing the arrows correspondingly here on this side. Okay, and then you just count how many times this vector rotated. Okay, so how many revolutions, like how many full revolutions that this vector did before returning to the original spot. Okay, so like the vector A started like this, right? And it goes back to this location, right? So how many revolutions did the vector did? Good, it did one. So like what you do is like count. So you walk along, along the circle once. And count how many revolutions the vector does as you moved. And the index of the vector is called, that the index is just this number of revolutions. So what I'm saying is that in this example, the index is 1. So in our example, index is 1. Okay. So just to make this a little bit maybe less confusing, let me go to GeoGebra again. Can everyone see it? Let's see. Okay, I think it will be this one. Can everyone see the GeoGebra thing? So basically, I'm showing you the, I mean, I should put this to, sorry. Just to make this a little bit more clean. So I'm basically showing you like the arrow that we care about, which was the arrows that I was drawing at the origin. So can everyone see? It's the purple arrow. I don't can. Let's do this here and do this here. Can everyone see the purple arrow? So like what I'm saying, like imagine a time this t is representing the point on the circle you are in. This is sort of like the angle. I mean, I started it a little bit off, but you know, a circle has 2 pi for the full revolution, so it takes you time 2 pi seconds, say, to get back to the beginning. So this is what was happening as you moved along the circle, right? And so that the arrow did like a one complete turn, right? And so that's why we would say that the index is 1. On the other hand, like, let's think about this one. Like, imagine that I had drawn a vector field for which the arrows behave as follows. So how many revolutions did the arrows? 2. So the index you would say is 2, okay? How many revolutions happen now? Let me repeat it. How many revolutions? Just one, but you know, did you notice something with the relative to the first one? It was this time, right? Good, perfect, beautiful. It was originally it was counterclockwise, right? This one was clockwise. So the convention is that it counts. If you did the revolutions counterclockwise, you say it's +1. If you did them clockwise, it's -1. Is that okay? So for example, here, 1, 2, 3, but they were 3 clockwise, right? So you would say that the index was -3. And so in general, like you can imagine drawing vector, like the point is that the arrows can actually just do things where they just like behave that way. And so they never, like they can, like what I'm trying to say is that the index would be like, can be positive or negative. Let's try to do something like a little bit cuter. Why would you say the index was here? Or let me make it easier. Good. Right, these ones are 0 because you're never completing a full revolution, right? So the index can also be 0 as well. Does that make sense? So like what I'm trying to say is that, so what I'm saying is that, just to go back to the iPad. What I'm saying is that, like the index this one can be positive if the number of revolutions is counterclockwise. And negative if the revolutions are done clockwise. And it can also be 0 if the number of revolutions happen. I mean, if there are no net revolutions, so no net revolutions. Okay. And so the cool thing is that, so you can imagine having like, so for example, you could have like a surface like this. And you could have like a stationary point here. And then you have like some vector fields, right? And you have like a vector field of the surface. Think of this as now a wind field. So it maybe it's telling you like maybe the velocity of the wind. And maybe you have here another stationary point on the surface. And it does something like that. And there's another great theorem that says that this is called the Poincare L8 theorem. Which says that the sum of all the indices of the stationary at each stationary point, you can compute the index. So at each stationary point, you can compute the index. And the sum of all these indices gives you back the Euler characteristic of the surface. Which is actually pretty cool. In fact, just so that you see why this is so interesting, I don't know if you remember, like you could imagine that I take a piece, a square, and I draw these vectors, this vector field. So it's a vector field that just, oh, I mean, yeah, you would need to like, I mean, at each point you would need to sort of like do something similar to what we did. Like you draw like a small loop and see how much times the arrows twisted about that point. You need to like work, like, you know, like say, for example, to figure out the index at this point, imagine drawing like a tiny loop there, you zoom in, right? And you think of secretly as like this being almost like the origin, like it's almost flat. So you think of it as being at the origin. Oh, there's like, I mean, there are different ways to find it. You can integrate. There are ways to find it that requires you to do like an integral, for example. You can integrate something and the answer of the integral will give you the index. Like there are more numerical ways to find it. I think that's what you're trying to ask me, right? Yeah. Like there are actual formulas for the index. I'm saying it visually because, like, you know, this is all related. Everything is related. Yeah. But yeah, there are like actual formulas for the index. Yes, like mathematical formulas. Yeah, not just like visually, right? But like if you think about this, right? Like imagine like closing this rectangle up. You have to it could be more than one. I agree. It's not entirely clear. I mean, the picture may not, I mean, it's not just that you look at the picture and it's maybe entirely obvious just from the look at it. Like you have to like actually I mean, you would need to sort of do this thing about translating the vector to this point so that you actually see how many times it revolved. I would not say that there's something like that you just look at it like without doing that and then you just say, oh yeah, sure, the index is 1 or 2, because it can be more complicated to figure that out visually. Yeah. But yeah, you could like naively I think that the index is 1 and actually ends up being 2 when you do the count accurately. But I don't know, like, can everyone see like how the arrows, like what I'm trying to say is that if you close two sides of the rectangle up, the arrows now look like this, right? Is that clear? Imagine having drawn these arrows on the pieces of paper, and then you just like you just glue these two opposite sides together, right? And now the arrows look like they're like sort of like just rotating. Is that making sense? And then like what I'm trying to say is that you could also then like close these two sides together, and then you get yourself like a vector field on the torus, right? And then you close these two together, glue these sides. And you'll get a vector field on the torus, on the donut, that never vanishes. Because at every point we drew an arrow with a certain size. Meaning that this vector field has no stationary points, right? So meaning that there are no stationary points. And since there are no stationary points, there are no indices to add, because the index is only defined at a stationary point, right? So the sum, like the sum of nothing is 0. So that tells you that the Euler characteristic of the torus has to be 0. So no indices to add. So that means that the Euler characteristic of the torus is 0. Is that making sense? But this is like a very interesting way to find the Euler characteristic. In fact, you can use it in the opposite way, what's called the contrapositive, meaning that if the Euler characteristic of a surface is not 0, then that means that the vector field has to vanish somewhere. So that's like usually the more interesting way to state it. So if the Euler characteristic is not 0, then the vector field must vanish somewhere. Right? Because if it vanished nowhere, then there would be no indices to add and you would get 0. So the way in which this is usually stated is that on this, like for example, on the surface of the sphere, I mean, it looks the same in the sense like if it has negative Euler characteristic, it just means that like there are more points with negative index than positive index, right? Like because the index could be negative, right? But like the important point is that it had to have points where the surface where it had to have stationary points. So the way in which this is usually stated, like is that for the sphere, right? So remember that the sphere has Euler characteristic 2, which is not 0. So that means that on the sphere, if you draw a vector field, it must always vanish at least at some point. So it doesn't matter how you try to draw a vector field on the sphere. Any vector field you draw on the sphere must vanish at least somewhere. And that's usually the way in which this is usually stated is that, for example, there's always a point on the surface of the Earth where the wind is 0. Is that making sense? If you think of the wind as a vector field. But if the planet were like a donut, you could have like a wind that's always with non-zero speed. Is that making sense? But this is like actually like a very cool result, right? Like something like if you think about how the Euler characteristic business started, it started with graphs, right? It started with this problem about the bridge, right? we did it for graphs, and then I'm telling you this also is related to the curvature of the space, and it's also related to how vector fields are supposed to vanish or not. So you see, like, this Euler characteristic concept is a very powerful concept. It sort of controls a lot of the information of what you can do on your space. Is that making sense? And so, like, now we have a lot of tools in place. So I think like that for the next two final classes, I'll start telling you a little bit more about. I think we more or less have a better understanding of how two-dimensional universes behave. So I'm going to tell you next time a little bit more like preparatory stuff, so that you understand a little bit of how the Poincare conjecture was proven. We'll try to talk about that last day of class, but at the very least, now you have, I think, an idea of somehow, like, you should get like the feeling that this is sort of like a very different way of thinking than the usual math classes that you are used to, right? You see, like, the types of questions you ask are like of a very different nature. They're more like, in a sense, qualitative, or so. At least, like, this is showing you that there's like other different perspectives, like to study objects in mathematics. Okay, so next time we'll talk about a little bit about flows, and that will actually set the stage to discuss the proof of the Poincare conjecture in the last class. Okay, so I think this is a good place to end, probably. Okay, good. I'll see you next Wednesday. You too. You too.